So hello everyone. In this class, we are going to discuss analysis of singly reinforced section by using limit state method. So one by one, we will discuss everything from scratch. First thing, you are very familiar about it. The concrete is weak in tension. We all know that concrete is good in compression but weak in tension. Concrete is weak in tension. So we have to give strength to concrete in tension zone. So we have to give strength concrete in tension zone. So we will discuss here only. We will discuss then only we will design this beam. Okay, we will discuss here. What I told you, if I take a simply supported beam means one end is hinge and another end is pillar. Okay, and one concentrated load is acting on it. What will happen? The beam will bend like this. The beam will bend like this. Means you already studied in your strength of material. When load is applied on your beam will bend, sagging or hogging. So bending stresses will come. Okay. So if beam will bend like this, sagging will happen. Then uppermost portion is your compression and bottommost portion is your tension. Uppermost portion is compression, bottommost portion is tension. When you are using a plain cement concrete beam, means in your whole beam only concrete is there, and we all know that concrete is good in compression. Okay, so when you are using a plain cement concrete and we are applying a load, the beam will bend and you will see that cracks are coming in tension. Cracks are coming in your tension zone because concrete is weak in tension. Concrete is weak in tension. So now what you have to do? You have to provide reinforcement in your tension zone. If we provide reinforcement in tension zone only, it is called singly reinforced section. But when we provide reinforcement in compression as well as tension, it is called doubly reinforced section. Okay, when we provide reinforcement, here I will write it. What is singly reinforced section? Here I will write it. Singly reinforced section. Okay. Here I will write it. Here reinforcement is provided only on tension zone. Only on tension. Here we will provide reinforcement, means we will provide steel only on tension zone because concrete is weak in tension. So we will provide steel in tension zone. Is it clear now? So we got to know that singly reinforced section is a section where reinforcement is provided in tension zone. So now you can see that this is the cross section of a beam and this is B is the width of a beam. Okay, I will write here, this is your width. B is the width of your beam. C is your overall depth and this D is your effective depth. What is effective depth? What is effective depth? What is effective depth? Effective depth is nothing but overall depth minus effective cover. Effective cover. Okay, effective cover. This is your effective cover. This is your effective cover. You already studied it also. What is clear cover? What is effective cover? This is your effective cover. Okay, so this is D, not D dash. This is your D, small d, and small d is your effective depth. Small d is your effective depth. Okay, small d is your effective depth. Effective depth. And we provided reinforcement, we provided steel in tension zone because it is a singly reinforced section. So we provided 3 bars of certain diameter here. So when we will calculate it, means if you are taking one certain diameter like 20 mm, and you will take the area pi by 4 into 20 square and 3 bars here are there, you will multiply it, you will get area of steel. What is AST? Area of steel. Area of steel. Okay. And here you can see that this is your neutral axis. This is what? This is your neutral axis, which is dividing the whole cross section into two parts. This is compression, this is tension, because when you applied load on a beam, it will bend. Topmost portion is compression, bottommost portion is tension, and we are providing reinforcement in tension zone. Again and again I am repeating, because this is very new topic to you. You have to understand everything is important, because definitely in GATE exam you will get one question from this topic. One question will come, that is moment of resistance. You can see in all your previous years questions of GATE, 2 marks question or 1 mark question is definitely coming in your exams. Okay, so it is very important topic. Okay, so the next thing is we are designing a beam, and that is a singly reinforced section beam by using limit state method. Already in previous classes I told you between the difference method. One is working stress method and another is limit state method. Limit state method design is totally based on strain concept. And for working stress method, already you designed in your previous classes the whole beam, that is totally based on WSM method, working stress method, totally based on stress concept. LSM is based on strain concept. One more thing you have to tell, what is that? Limit state method has limit state of collapse and limit state of serviceability. Okay, what is limit state of collapse? What all the things comes under limit state of collapse? That is your bending, that is then compression, then shear, then torsion, and in serviceability there is vibration, there is cracking, okay, there is deflection. All these things come under serviceability. We have already studied this. Okay, but here what we are doing, we are analyzing a singly reinforced section by using limit state method, and limit state method is totally based on strain concept. So before designing a singly reinforced section, you have to know about assumptions used in limit state method. Then only it is possible to design or analyze this singly reinforced section. So you have to know about the assumptions used in limit state method. What are the assumptions we generally use? And definitely you can see there are so many questions coming from this topic in assumptions also. Okay, so we will one by one discuss all the assumptions. Okay, all the assumption. First assumption, assumptions used in limit state method. What is your first assumption? What is your first assumption? First assumption, plane section before bending remains plane even after bending. Remains plane even after bending. What this means? What does it mean? Plane section before bending remains plane even after bending. Suppose, by example I will explain you. Again I am taking a simply supported beam. One end is hinge, another is roller, and you are applying a concentrated load P or W. Okay. So now what will happen? This beam will bend. This beam will bend like this. Again sagging happens. Your neutral axis. Here bending stress in neutral axis or bending strain is 0 in neutral axis, and you already know that it will vary linearly. So topmost portion is compression, bottommost portion is tension. So beam will bend like this. Beam will bend like this. Okay. So earlier if you take the cross section of a beam, it is coming like this rectangle section, your B, your overall depth. But after bending, topmost portion, what is experiencing? It will, what is happening? Compression is coming in topmost portion, and bottommost portion, tension is coming. So the cross section will come like this, like a trapezoidal. This is practically, or actually this is happening. Before bending, it is a plane section. After bending, it is not a plane section. This is your practical condition. This is your practical condition. But if you consider this practical section, your strain, variation of strain throughout the cross section is not linear. It is non-linear. Means variation of strain is not linear, non-linear, because of this. So what we considered? We considered that plane section before bending remains plane even after bending. Means it will not come like this. It will come plane only. So now we can say that plane section before bending remains plane even after bending. It means variation of strain throughout the cross section is linear. Means variation of strain throughout the cross section is linear. How it is possible? How we can say that? By telling that plane section before bending remains plane section before bending remains plane even after bending. Okay, so now we can say that the variation of strain is linear throughout the cross section. Variation of strain is linear. Okay, variation of strain throughout the cross section is linear. I will show here. Here I can show you. Okay, here your strain diagram, because LSM is totally based on a strain diagram, and it will come like this. Variation of strain is neutral axis. So your neutral axis, and this is your depth of neutral axis. XU is your, I can write here, XU is depth of neutral axis. XU is depth of neutral axis. This is your strain diagram. Okay, strain diagram, and it is linear. Because plane section before bending remains plane even after bending. So it is what? Okay. Now, next, second assumption. This is your first assumption. Second assumption. What second assumption tells? Maximum compressive strain in concrete at outermost fiber should be 0.0035. Sir, how it is possible? So it is written in your code. What is your code for RCC? It is IS 456,000, Indian Standard 456 2000. 2000 is the year where upgradation happens. Okay. So now this is your diagram. In this diagram, this is the strain diagram, and strain is varying linearly, and there should be some value in the outermost compressive zone, okay, for concrete, and it is Maximum strain for concrete in outermost zone, it is 0.005. 0.0035. Very important. Each and every concept is very important. Maximum strain in outermost fiber is 0.0035. 0.0035. Definitely in your prelims exam, in your ESE prelims exam, or in your GATE, 1 marks question is coming from these topics. Okay. Now, next, third assumption, you have to know about maximum strain in your steel, maximum strain in your steel, or maximum strain in your tension zone, in your outermost fiber. Okay, because what is there in tension zone, steel is there. Okay, so now third assumption, okay, that is maximum strain in steel at outermost fiber should not be less than 0.002 plus 0.87 Fy upon S. Means it should not be less than, means it should always be greater than or equal to 0.002 plus 0.87 Fy upon Es. Means it should always be greater than or equal to 0.002 plus 0.87 Fy upon Es. So here I will write it should always be greater than or equal to 0.002 plus 0.87 Fy upon. This is your value of maximum strain in steel. It should not be less than, it should be greater than or equal to 0.002 plus 0.87 Fy upon Es. It should not be less than, okay, by this value. And maximum strain in concrete, that is 0.005. First assumption, strain section before bending means strain even after bending. It means strain should be linear throughout the cross section. Second assumption, maximum compressive strain in concrete, it should be 0.0035. It is a fixed value. Then maximum strain in tension zone for steel, it should not be less than, means it should be greater than or equal to 0.002 plus 0.87 Fy upon Es. Then how you got this value? How you got this value? Okay, I will explain you that. How we got this value. Okay. Here. So what we got the value? That is 0.002 plus 0.87 Fy upon Es. So already you studied in your strength of material that what is modulus of elasticity? That is stress upon strain under elastic limits. Okay. So now the whole singly reinforced section we are designing with a strain concept, because LSM is totally based on strain. Okay. So we will write strain is equal to stress upon modulus of elasticity. Okay. And you already know that design strength or design stress is equal to characteristic strength upon factor of safety. So here what is your characteristic strength or what is your characteristic stress? That is your Fy, that is your yield stress. Okay, that is your yield stress of a steel. This stress value, I am talking about this stress value, yield stress of a steel, because we are discussing about steel, yield stress of a steel, divided by factor of safety. And what factor of safety we use for steel in limit state method? We use 1.15. What we use? 1.15. Okay, so I will write here 1.15. So when you will solve it, you will get this is Fy, I can write here Fy upon 1.15 into ES. So when you will solve it, you will get 0.87 Fy upon ES. This is how we got this value. This is how we got this value. Sir, how you got this value? How you got this value? So this is also you studied in your strength of material. When you draw a stress strain curve and the material is less ductile, okay, so you will not get a specific yield point. So to get a specific yield point, you draw a tangent, and that is at 0.2% proof stress or proof strain 0.2%. Okay, proof strain will draw. Okay, will draw tangent like this in your stress strain curve. You are not getting specific yield point. What you will do? You will draw a tangent that is 0.2%. Okay, so from there you got this value 0.002. 0.00. Okay, so this is how you got 0.002 plus 0.87 Fy upon ES. And what is ES? Modulus of elasticity of steel. What is ES? Modulus of steel. And you also you are very well known about it. Very well know this value. This is 2 into 10 to the power 5 megapascal. So now what I will do? I will take different grade of steel. I will take different grade of steel like Fe250. This is your mild steel, plain bars. It is more ductile than Fe415. This is your HYSD bar, high yield strength deformation bar. Then Fe500. Then Fe500. Okay. Now I will write all the maximum strain for these grade. Maximum strain in steel. Okay. For different grades. What is the formula? What is the formula? Now you know the formula. This is your formula. So you will write 0.002 plus 0.87 Fy upon S, and you will put the value 0.002 plus 0.87 into 250 upon 2 into 10 to the power 5. Now, what value you are getting? You will get around 0.00308. This is the maximum strain value. Maximum strain value for steel when you are using grade Fe250. Now similar for other grades. For other grades, if you are using 0.002 plus 0.87 Fy upon Es, you put 0.002 plus 0.87, grade of steel is 415 upon 2 into 10 to the power 5. Now by solving with your calci, you will get one answer that is 0.00388. This is your value for Fe415. This is your value for Fe415. This is for Fe415. This is for Fe250. Okay. Now another one. If you put 0.002 plus 0.87 into 500 upon Es, when you solve it, you will get near about 0.00417. Okay. So for 250, you are getting maximum strain value in your tension zone. For steel, it is 0.00308. For Fe415, you are getting maximum strain for your steel, it is 0.00380. And for Fe500, you are getting 0.00417. Okay. So all these values depends upon grade of steel. So definitely one question they will ask, what is the maximum value of strain for concrete and for steel when you are using grade Fe415? What will be the answer? Think and answer. So maximum strain for concrete, it is fixed value 0.0035, and for steel, if you are using 4 on 5, you can easily say that it is 0.00380. It is 0.00380. And for 500, it is 0.00417. And for 250, it is 0.0030. Got it? Got it? Now, this is your third assumption. Fourth assumption. Fourth assumption. What is fourth assumption? What is fourth assumption? Tensile strength of a concrete is ignored. Means when you will design a singly reinforced section by using LSM, you have to ignore tensile strength of concrete. Means while designing, we will not consider tensile strength of concrete. Practically, little bit tensile strength is there. You have already studied in your hard property of concrete different strength like characteristic compressive strength, then modulus of rupture, bending strength, then your tensile. There also direct tensile strength, indirect tensile strength. There you studied that. Okay. But while designing in assumptions, what we did? We have neglected the tensile strength of concrete. We have neglected it. Okay. This is what fourth assumption. This is what fourth assumption is. Now, next thing, fifth one. What is fifth? Fifth is for design value for stress strain curve means it is a design stress strain curve. For it is not normal stress strain curve, it is design strain curve. For design stress strain curve up to 0.002 strain value, up to 0.002 strain value, stress strain curve is parabolic, and up to 0.0035 it is constant. Means for design stress strain curve up to 0.002 strain value, stress strain curve is parabolic, and up to 0.0035 it is constant. I will show you here. Your stress strain curve, here strain, this is your stress, because strain is a independent and stress is a dependent. Stress is based on strain only. Deformation, you will see deformation, you will get the value of strain. Okay. So here the value is 0.002 strain value, and here value is 0.005. This is the strain value. What this assumption told me? Up to 0.002 stress strain curve is parabolic, and up to 0.0035 what it is I will draw again because diagram is short. Again draw it. I will draw in next page. Your stress strain curve, design stress strain curve, design stress strain curve. Okay. So up to up to 0. Up to 0.02 strain value, so up to 0.002 it is parabolic, and up to 0.0035 it is constant. This is your stress strain curve. This is your design stress strain curve. This is your design stress strain curve. Up to 0.002 it is parabolic, then it is constant. Now I will show you stress strain curve here. Now I will show you stress strain curve here. I will show you stress strain curve here. Your strain diagram, now stress diagram. Now stress diagram. Okay. This is your 0.0035. I will write here. This is the value of 0.00 strain value. Okay. And I will write mention A, B, and C. Now what I will do, I will draw the stress diagram. Now what I will do, I will draw the stress diagram. Stress diagram. So up to 0.002 it is parabolic. Here it is written. Here already it is written. Up to 0.002 strain value, stress strain curve is parabolic, and up to 0.0035 it is already given. It is already mentioned in your assumption. Okay. So it is parabolic up to 0.002. Then it is coming constant. This is your stress value. This is your stress diagram. And topmost portion is compression, bottommost portion is tension. Okay. So now you can tell that here one compressive force is acting C, and here one tensile force is acting. This is compressive stress, tensile stress. This is your compressive stress, okay, and this is your tensile. Compressive force, your compressive force, and this is your tensile. Okay. So now this is your stress diagram by using this strain diagram. Up to 0.002 it is parabolic, then it is constant, then it is constant. Okay. Then it is constant. Okay. Now what we will do, we have to know this value and we have to know this value. What will be the value here and what will be the value here? Then I will explain you another thing. Okay. So we already know that the characteristic compressive strength of a concrete is FCK. The characteristic compressive strength of a concrete is FCK, means the strength below which not more than 5% test results are expected to fail. Okay. And generally this value, when you test the compressive strength for cube testing, you will get this value. By using cube testing in a machine, you will get characteristic compressive strength. But when you take lab testing, lab for beam and all, what you have to do, you have to take the design value. And what is the design value? Characteristic strength upon factor of safety. Characteristic strength upon factor of safety. So what I will do, I will divide this characteristic compressive strength by factor of safety. And what is the factor of safety we are taking for concrete? We are taking 1.5 as a factor of safety. So when you will divide this FCK with 1.5, you will get 0.67. This is how you got this value, 0.67 FCK. Okay. But when you go for site, when you go for site, this is for lab, okay, this value is for lab, but when you will go for site, you already know it, the quality control of concrete is poor, it is very fluctuating, okay. So now what you will do, again you will divide this 0.67 FCK with 1.5. Again you have to divide because quality control of concrete is very poor. Okay. So now which value you will get? You will get 0.45 FCK. This is the stress. This is the stress of concrete. This is how we got this value 0.45 FCK. This is how we got this value 0.45 FCK. 0.45 FCK. And now I will write this 0.45 FCK here. The stress value 0.45 FCK. This is the compressive stress of concrete 0.45 FCK. Means first characteristic compressive strength you got by cube testing. Then for beam and all, another in your lab test, again you divided with 1.5 factor of safety, you got 0.67 FCK. Again when you go for site, because quality of control of concrete is very poor, it is very fluctuating, so again you have to divide it with 1.5. And now what is the value of stress you got? 0.45 FCK. This is how you got the value of 0.45 FCK. And what is the value? What is the value of stress? Tensile stress. Tensile stress. Tensile stress. What is the value of tensile stress? How you got the value of tensile stress? It is very easy. You already did it. Fy upon 1.15. Characteristics strength of steel divided by factor of safety. And what is the factor of safety for steel? 1.15. And you got the value of 0.87. This is the tensile stress of steel. Tensile stress of steel. This is the this is the compressive stress of concrete. Compressive stress of concrete, and it is 0.45 FCK, and it is 0.45 FCK, and this is 0.87 Fy. This is 0.487 Fy. This is tensile stress of steel. This is compressive stress of concrete. Okay. Now in further class, what we will do? We will analyze this diagram and we will determine what is compressive force, what is tensile force, what is the lever arm. I will explain you what is the lever arm. What is the lever arm? Here also one value is there. What is the value? यहाँ पे कौन सी value? What is the value? Okay. So in next class we will discuss compressive force of concrete, tensile force of steel, and what is the lever arm. What is the lever arm? By using this, we will know the formula of moment of resistance. And definitely in your GATE exam, you will see one question is there for moment of resistance. So for that, you have to know all these diagram, all the basics from scratch. I told you. This is the diagram for singly reinforced section. By analyzing, by designing with limit state method. So what I told you, limit state method totally based on what is singly reinforced section. Singly reinforced section is a section where we provide reinforcement in tension zone. Here I provided in tension zone. Okay. This is your XU. This is your depth of neutral axis. Topmost portion is compression. Bottommost portion is tension. Okay. LSM is totally based on strain. Okay. So here strain diagram came first. Next, assumption plane section before bending remain plane even after bending. It means strain should be linear throughout the cross section. Here cross section is linear. Maximum compressive strain in outermost fiber in concrete is 0.0035. It is fixed value. Then maximum strain in outermost fiber for steel it should not be less than, means it should be greater than or equal to 0.002 plus 0.87 Fy upon Es. Next assumption, tensile strength of concrete is ignored. Okay, so here tensile strength of concrete is ignored. Design stress strain curve up to 0.002 strain value, it is parabolic. Here you can see it is parabolic. Then it is constant up to 0.0035. Okay, got it? Here we got the stress value of concrete, that is 0.45 FCK. Here we got the stress value of steel, that is 0.87 Fy. So in next class we will analyze this diagram again and we will solve one problem by using all that formulas: compressive force, tensile force, moment of resistance and all. So I hope you understood all these topics. If any doubt is there, you can ask me, I will explain you. Okay? Thank you.